Alex Baina here, and welcome to our first lesson in thermodynamics, thermal energy. Thermal energy. Thermal energy is detected by a thermometer. The first thermometer was invented by Galileo Galilei in 1593. This thermometer is called thermoscope. It is operated using water. The second thermometer, or the mercurial thermometer of today, was invented by Gabriel Fahrenheit in 1714. A thermometer reads the temperature of a substance. The two units for temperature scales are Fahrenheit and Celsius. Let us now examine the two units used in temperature scale. First is the Fahrenheit. In a Fahrenheit scale, the freezing point of water is 32 degrees Fahrenheit, while the boiling point of water is 212 degrees Fahrenheit. Celsius scale was developed by Anders Celsius. He invented the centigrade scale in 1743. In a Celsius scale, the freezing point of water in a Celsius scale is 0 degrees centigrade, while the boiling point of water in a Celsius scale is 100 degrees centigrade. Here is a comparison between a Celsius thermometer and a Fahrenheit thermometer. You notice that water freezes at 0 degrees centigrade. That is equivalent to 32 degrees Fahrenheit, while water boils at 100 degrees Celsius. That is also equivalent to 212 degrees Fahrenheit. The Kelvin scale is derived by adding Celsius with 273.15. Kelvin is the absolute temperature. William Thomson, also known as Lord Kelvin, developed the Kelvin scale and the concept of absolute temperature. In thermodynamics, this is the temperature at which a system has the lowest energy. This is negative 273.15 degrees Celsius on the Celsius scale and negative 459.67 Fahrenheit on the Fahrenheit scale. In other words, absolute temperature, or absolute zero, is the lowest possible energy or thermal motion a matter can reach. Absolute zero is impossible to achieve. Basically, it is conceptualized for the basis of reference. Going back to thermal energy. Thermal energy can be absorbed or emitted by a substance that is dependent on the substance's specific heat capacity. Heat capacity is given by the unit Joule per Kelvin. Another name for heat capacity is also known as thermal capacity. So what is the concept of heat capacity? This is actually the amount of heat to be supplied to an object. If the heat capacity of a particular substance divided by its mass, then that is the specific heat capacity of that substance, given by the unit Joule per kilogram Kelvin. The formula for specific heat capacity is equal to delta Q, that is equal to mass times specific heat times delta T. Q, or delta Q, is the heat that is lost or absorbed by the object or substance, while mass is the substance's mass and C is the specific heat of that particular object or substance, while delta T is the change of temperature by the formula final temperature minus the initial temperature. Here is a table of the specific heat capacities of different substances. Example here are air, aluminum, beryllium, cadmium, carbon dioxide, helium, and other substances. The substance with the highest heat capacity here is helium. It has a value of 5.1932 joules per kilogram Kelvin. Let's try this problem out. Supposing we are going to heat the water. Question letter A. How much heat is required to raise the temperature of a 250 ml water from its initial temperature, which is 20 degrees centigrade or Celsius, to its final temperature, which is 35.0 degrees centigrade. Letter B. How much heat is lost by the water as the water cools back from 35 degrees centigrade to 20 degrees centigrade. Since the amount of water inside the casserole is 250 ml, and that will have an equivalent mass of 250 grams because 1 ml of water is also equivalent to 1 gram. The specific heat for water is 1 calorie per gram times degrees centigrade. Our formula is delta Q, that is equal to mc delta T. And so we are going to replace all the missing values in here from the given problem. The letter A question is asking for the heat. So what will be the heat requirement if we will raise this amount of water, 250 ml, to 35 degrees centigrade from 20 degrees Celsius? Therefore, the mass is 250 grams times the specific heat of water is 1 calorie per gram degrees centigrade, multiplied by the change in temperature, that is equivalent to the final temperature, which is 35 degrees centigrade, minus the initial temperature, which is 20 degrees centigrade, and that will be equal to 15 degrees centigrade. And the answer is 3.75 times 10 raised to the power of 3 calories. However, we can also convert these calories into kilojoule, and I will be showing you the conversion later. So 3.75 times 10 raised to the power of 3 calories is equal to 15.7 kilojoule or kilojoules. Now, letter B question is asking us how much heat will be lost if we'll allow this casserole with water that is already 35 degrees centigrade to cool down back to 20 degrees Celsius. The same formula will be applied. How much heat will be lost? While earlier, we are asking for how much heat will be added. Okay, so we will again replace the missing values with the values given in our problem. So we have delta Q is equal to mc delta T. And therefore, our M, the mass is equal to 250 grams times C, which is equal to 1 calorie per gram degrees centigrade, multiplied by the change in temperature, which is the initial temperature is 35 degrees Celsius and the final temperature is 20 degrees Celsius. In other words, 20 degrees Celsius minus 35 degrees Celsius will become negative 15 degrees Celsius. Now, the negative here simply means that the final temperature is much lower than the initial temperature because heat is lost from the system, which is water in this case. And so the value is equal to negative 3.75 times 10 raised to the power of 3 calories. That will be also equal to negative 15.7 kilojoules. Negative simply means that heat is removed from the system, and the system is the water that we boil in the casserole. The conversion of 1 calorie to joule is equal to 4.19. So in other words, 3.750 times 10 raised to the power of 3 calories is equivalent to 3,750 calories. And we are going to convert these calories into joules. And that is equal to 3.750 calories times the conversion factor, which is 4.19 joules in every calorie. So we can cancel out calorie, and the answer would be 15,712.5 joules. So 15,125 joules can be converted into kilojoule by dividing this value with 1,000 joules. So cancel joules, and the value would now be 15.7 kilojoules. So the concept of specific heat capacity is actually the amount of heat that will be needed to raise the temperature of a substance that has a mass of 1 kilogram. An example to this specific heat capacity is that of water. Water can be raised from 1 degree to another degree if we apply a heat that is equivalent to 4,200 joules in every kilogram of that water. Speaking of thermal energy, that can be visualized by the kinetic energy of gases. The kinetic energy is an energy in motion, the motion of gases that involves the speed of the molecules of gases. As seen in the illustration, gas moves rapidly in straight line. Gas do not have an attractive or repulsive force. And you also notice that gas molecules are very far from each other. But if we are going to collect all these molecules of gas together, they will just occupy a very small container. So to talk about gas, the gas possesses an initial kinetic energy since the molecules are moving. This is called kinetic energy, or the energy of motion. This is the gas internal energy. They can be designated by the symbol U. U is the internal energy of the gas. The kinetic energy of that gas is also called the internal energy of the system. The system here is the gas. The kinetic energy of that gas can increase, for example, if we apply heat into the gas. As heat is applied, temperature also of the gas increases. Thus, the kinetic energy also increases. The pressure of the gas will push the walls of the container. If a piston is attached, the piston can move a significant distance. Work is generated in here. Work is equal to force times distance. Work is given by the symbol W. Work is done by the system or by the gas. This is how an engine combustion works. Fuel is atomized and ignited to produce a high-pressure gas, which make the piston to move back and forth inside an engine, thus drive the vehicle. Heat transfer is also involved in the kinetic energy of gas. The types of heat transfer are radiation, conduction, and convection. Going back to thermal energy can cause thermal expansion of some objects. Thermal energy can also change the state of matter. These are solid, liquid, and gas. Under the pressure, volume, and temperature relationship, this gas can be described by the governing law of the gas laws.